¿Somos todos ya? Parece que, bueno, ok. Bueno, nada más para aclarar el gran debate que ya está volviendo de guerra. Ok. Muy radical, esos 97.
Ah, okay, awesome. Should we start? Okay, so I wanted to say actually one thing that I should have said at the beginning. So it turns out that I started working on monsoons in a place like UCLA, where of course we had David Nealon, who had been working on monsoons for quite a few years. But I actually did my PhD together with Bjorn Stevens, who was not working on monsoons at all. He was working on the low clouds, the stratocumulus clouds that we heard of quite a few times here. And he really was well known already in the community for his um, smaller scale modeling, LES modeling of important properties of these clouds. And he had started thinking more broadly about the large scale environment in which these clouds tend to form. And of course, the importance of the inversion that basically prevents any deeper convection. And those were the years where work by Hoskins also started catching everybody's attention. I think that there was the mention of Hoskins and Rodwell 1995, but no, actually, the papers that were mentioned were exactly the Rodwell and Hoskins paper that tried to emphasize, tried to explain the seasonal cycle of the Hadley cell and the fact that in the subtropics we have both the subtropical highs, so this area of large scale descent, and the monsoon systems over the continents. And they really made through, again, very simple dry dynamical models in which the diabatic heating from monsoons was imposed as a forcing to the dry thermodynamic equation. They really showed how the diabatic heating due to monsoons explains a large fraction of the descent to the north and west, I should say, to poleward and westward of the monsoon heating region, which also explains why the subtropical highs are stronger during the summer. And usually there is attributed to the Hadley cell, but as we have seen, the summer cell, so the zonal mean descent is very weak during the summer. So it must be some other mechanism. It's primarily a stationary wave response to the monsoon heating. And so Bjorn Stevens was working primarily over the Pacific region. He had just led a field campaign to study the stratocumulus region there. And so we started thinking about the possible interactions between the North American monsoon and the subtropical high over the Pacific. I was a second-year PhD student at the time. I took a mesoscale meteorology class with Roger Wakimoto. And as part of the class, we needed to do a project, a research project. We would write a short review of the literature and then present what we had learned as a final presentation for the class. And I decided to look a little bit at the literature of the North American monsoon, because that is when I had started thinking about these possible interactions. And one of the papers that, of course, the paper really at the time was the one by Dave. And so I thought that the North American monsoon in itself was so interesting that, in fact, my first two papers were really just focused on some observational features of the North American monsoon at the time. Quickscat data, scatterometer data had become available. We had a few years at the time with high enough resolution to start saying something about, for instance, the climatological winds over the Gulf of California. And so my very first study was, in fact, showing that this reversal of the winds over the Gulf of California, that at the time was really, people had been discussing that as part primarily of data collected during field experiments. So we had a few years where we could show that that was actually a climatological feature. Then I started thinking about more broadly about monsoons, and I never made to really think about the connection between the North American monsoon and the Pacific subtropical. So I thought this was an interesting story to tell, because, again, I spent a lot of time actually thinking. And again, the paper by Dave was a great review. And that was really a great starting point to learn more about this system. And then I slowly steered towards larger scale monsoons. Well, the truth is that also the research that you do is also influenced by people you meet. And I also had the pleasure to meet and interact with Tapio Schneider at Caltech, who's definitely very large scale. And in fact, a lot of my more idealized work has been definitely inspired by Tapio in many influential ways. The other thing that I wanted to say is that today is my birthday. And I am turning 23. And it's really, again, I could not imagine a better way to celebrate it than giving 2 hours lecture. No, I'm kidding. Than being here. And in fact, I actually do love teaching. So in many ways, I think it's very fitting that I am spending my birthday, part of my birthday, really talking about things that I'm very excited about. Okay, so I have 2 hours. We'll see if we use them all. And this is where we actually are moving towards less pedagogical talks and more research-oriented talks. In fact, I'm going to show you results from 2 different research projects, ITCC monsoon related, that I've been thinking about in the past few years. And so the first one is, as was already mentioned a couple of times, yesterday by Spencer, today by Dave, I'll be showing you results of based on global models that are run at very high resolution. And this is work that I am doing in collaboration with Adrian and my postdoc, Sebastian Mueller, who's been hired on this project, which is NextGems. Before talking about the project, I wanted to put this into a little bit of a broader perspective, because I don't know, maybe this is obvious to everybody, but there is the sense in the climate modeling community that climate modeling might be at a crossroads. And what I mean by that, I simply mean that there is the sense that to really give the accurate information at the local scale that is needed by the end users, us policymakers, we need to do better. We just cannot keep using the tools that we have been using so far, the state-of-the-art climate models. And so this is a plot that was you already saw it yesterday. Spencer had it in his presentation. This is taken from an opinion paper by Tapio Schneider et al. And you see a few points that I will try to explain here. So here on the right hand, the right y-axis, we basically see computer performance in gigaflop. And this is what these blue dots, again, notice that this is a logarithmic scale. And notice how these dots, blue dots, represent the computer power of the highest, the top performing computers through the years, basically when climate modeling was in its early infancy. And the fact that this is a linear scale is just providing in this information that we all know very well, that this computational power is increasing exponentially following the Moore's law. And notice how, for instance, now this is where we are. Basically today, we're entering resolutions in which we might start being able to resolve some aspects of deep convection, not the individual convective towers and scales, but the more organized forms of convection. But notice how now our computational powers are a factor 10 to the 9 larger than the ones, for instance, used by Suki Manabe. Of course, this also raises an existential question for the community. Are we 10 to the 9 times smarter than Sumi Manabe was? I won't give you my personal answer to that. So then on the left y-axis, we have a measure of a horizontal resolution inverse per kilometer, also a logarithmic scale. And so if you go up on this y-axis, this represents increasing resolution. And so here you see that the yellow filled or open dots and the diamonds show basically the resolution of climate models, again, through the history of climate models. And as next generation of climate models were developed, the filled ones are atmospheric only, general circulation models. The open circles are atmospheric oceanic couple models. The diamonds are the Earth system models. So if all of that enhanced computational capability had gone into just increased resolutions, then all of these dots representing model resolution would lie on the one-to-one line. We see that this is only the case, and not for all of them, for atmospheric only GCMs. The other points lie below this line, and that is because, again, this enhanced computational power has gone into increasing complexity. And this is what I'm showing here in a schematic. Again, you see the evolution of climate models that started from atmospheric only. Then we started coupling the atmosphere to the ocean and some aspects of the cryosphere, all the way to the Earth system models that not only try to represent physical processes, but also other biogeochemical processes. But it has to be said that resolution, of course, has also increased to the point that Diamond was the first framework, provided the first framework to try to compare models that at global models run at high resolutions. And here we're talking about simulations that had to follow a certain setup, run for 40 days. Of course, we're not talking about climate scales. We're just talking about 40 days at less than 5 kilometer resolution. And this is a snapshot of the cloud field as simulated by these very high global models compared to observations. Can anybody tell me which of these is the observation? Does anybody want to? Well, if you don't know the answer, that is really the point here, right? This is really to show that now our global climate models are getting to resolutions that are high enough to be digital twins, to use a word that has become very common, faithful digital twins of what we can observe. So anybody wants to give it a try? Which one is the observations? It's obvious when I tell you. Of course, it's the one in the middle. Absolutely. That's the one in the middle. But again, it's hard to tell, right? It's a little bit hard to tell. Yeah, that's the one in the middle. Yeah. Okay, and so this is again to make this point as to how much more accurate at the local scale the information is. Again, here I'm showing just a schematic of the cloud field as represented by a climate model run at your typical CMIP6 resolution, let's say between 50 and 100 kilometers, and this diamond resolution, in this case, 2.5 kilometers. And so is high resolution the future? And this is really where the debate is happening in the community. And so here I'll quote Bjorn Stevens, my former PhD advisor and the director of the MPI, the Max Planck Institute for Meteorology in Hamburg. A real breakthrough in our ability to forecast the weather and to predict how the climate will change at regional scales is now in reach. This is largely possible due to the latest advances in supercomputing, including the emergence of exascale computing, and to the substantial efforts made in the last years in Europe to adapt our weather and climate modeling capabilities and their underlying infrastructures to novel supercomputing architectures. And it is true that in this respect, although there are worldwide initiatives, and the Japanese community has really done this for a while now, really the European countries are somewhat taking the lead in this high resolution initiatives in the climate modeling communities through a number of projects and enterprises. Again, the project that I'll talk about today is this EU-funded H2020 Next Gems project, with the aim of developing IFS and ICON as the next generation climate models, pushing them to very high resolution. We're talking about, again, kilometer scales globally, run, of course, not just for 40 days, 60 days, three months. We're really looking at least a few decades to say something about, of course, the climate, which is the statistics, the aggregate of many weather events. Destination Earth is another initiative that is worth of mention here. Is really the flagship initiative of the European Commission to develop a highly accurate digital twin of the Earth. Again, notice this word, digital twin. I had this conversation yesterday with Spencer. In reality, every model is a digital twin, right? It's a digital twin. Twin really emphasizes the fact that now we're getting to resolutions that become comparable to the resolution of observations that we have available. So now we can make better comparisons between the observed world and our modeled reality. I'll also mention two other German-funded projects, ERIE and Warm Worlds, again, used where they want to use these high-resolution models a little bit in different contexts. Warm Worlds is also looking at paleo climate.
Simona, can you get how much money is being used, being donated or dedicated to Next Gems? Just do you have an idea?
10 million.
That's it?
It's not
No, that's not much.
No, it's not much.
Oh, okay.
But within Destination Earth, there is a larger pool of money that is going to the modeling centers. ECMWF is really taking a lot of these things. And there are also broader initiatives, including EVE, that Adrian mentioned today, right, that is broader than just high-resolution modeling. It's really this vision. EVE stands for Earth Visualization Engines. And it's this idea that really need to bring forces together and invest on, if not, let's say, not only one, but basically, again, instead of dividing our forces across many different models like the CIMIP archive, but really focus our forces. This goes back to vision that Tim Palmer and others have had for years about a CERN for climate modeling. And again, this idea would be that the forces will all be used to develop a better model that could be used in different local centers, leveraging, of course, AI-based methods to also, again, use better observations. I'll talk a little bit about this, but of course, high resolution is great in certain ways. We will see that doesn't solve our problems. We have long ways to go, but the one thing that definitely right now you cannot do with the high resolution climate model or Earth system model is you cannot span the parameter space in a broad range of configurations. These are extremely expensive simulations, so you cannot, for instance, run a lot of tuning experiments. You cannot tune individual parameterizations because even at high resolutions, a lot of processes are still parameterized, so it's not the end of parameterizations. And also, you cannot run large ensembles. And so this is where AI-based emulators might come into play. So really this broad vision as to how, as a community, we could come together and then have centers distributed around the world where, again, again, all of this capacity that has been built by the community and then by local end users. Okay, I hope that was somewhat clear. Adrian is involved. I'm not involved directly with Eve. Next Gems, of course, is part of this bigger vision. So I do get updates, but I'm not particularly active on Eve. Okay, so then, of course, let me emphasize, and it's fun for me to show slides with very two different perspectives of where the future should go people really have influenced my career, both appear and they take opposite extreme views, right? So again, Bjorn Stevens is really very highly supportive of pushing climate models to high resolution. The other vision really leverages greatly AI, data-driven methods. And Tapio Schneider was maybe one of the first ones to really emphasize how probably the better way to go would be to use conventional climate models. So the same CMIP type resolution, where, however, the traditional parameterizations are being replaced by data-driven parameterizations, data being provided either by observations or by high-resolution models that could be short runs by global models or limited area models like LES. Of course, the question is then we still, again, that is one advantage of the high resolution approach is that, of course, you're getting to scales that are closer to the scale where the information is needed, again, for adaptation, mitigation, policies, and so on. With a conventional climate model, which is data-driven, you still have the problem of downscaling this information. And again, the downscaling could happen both through dynamical downscaling methods, or now, of course, AI has really become somewhat the word. And again, Tapio has been working on a project called Clima that really somewhat makes use of this general approach. In Europe, we have other approaches. And a lot of other people are just working on individual parameterizations related, for instance, to deep convection of ocean processes and mesoscale eddies. Okay, so is high resolution the future? I don't want to give you an answer here. Personally, think that in fact we probably need a combination of all approaches. And as I really have this concluding remark in my slides, I'm a firm believer that the model hierarchy is really the one that we need to use. We definitely cannot forget, despite the fact that we have high resolution, a lot of data, we cannot forget about theoretical development. Yes, Alejandro.
Oh, it's okay if I ask a question?
Oh, sure, absolutely.
It's basically something of personal opinion, because when you mention about the AI technologies, so all these methods are really improving the forecast, but it's not solving the problem of solving the equations and solving actually the physics. So we are kind of a problem that we have more economically speaking kind of models using AI, but we are defunding future projects.
I totally agree. And this is where the tension is, right? Here, the problem is that both AI-based approaches and high-resolution modeling require a lot of resources. And so that is really where the tension is in the community. Again, I am not in favor of either or approaches. I think we still have to wait and see a little bit how it all evolves. The one thing about the AI approaches for climate forecasts, that is an initial value problem, right? And so, of course, AI, if you have a large sample of training data, that's where, of course, we all know that now there are completely AI-driven forecast models that do as well, if not better, than dynamical models. When we think about, though, climate is not an initial value. Climate is a boundary value. Energy conservation is fundamental, right? Because it's really a response to changes. And this is where we need to be careful about even how we use AI to develop prioritization. Again, of course, people that are working on this are not stupid. They're very well aware of that. And so they're thinking about using parameterizations that do have some conservation properties. The other important point is that right now, this vision that is schematically represented here, there is no model that has been shown to work at the climate scale yet. Also because parameterizations that work well in isolation, you put them in a dynamical core, they tend to lead to instabilities. So that is to say that this vision is very ambitious, but it still has to be realized with all of the issues that you very rightly raised. It's a question of resources. Again, I think that you probably already, after hearing me speak for 2 days, and I think that this will keep emerging today as well, I'm very much in favor of, so I think that, again, that's what I like to do. I'm not saying that everybody should do it, but we should not forget about fundamental theories. And fundamental theories are, we will see, hard to test if you don't have the flexibility of running yet another simulation where you can change a parameter, perform denial mechanism experiments, and that becomes much harder if you don't have that flexibility. And so that flexibility, of course, requires tools that are less computationally. Other questions? So as you see, this conversation is really reflective of the tension that exists right now in the community. I went in October 2023 to the WCRP Open Science Conference, and there were very, very hot debates at that conference, reflective, again, the fact that there is the sense in the climate modeling community that we are at a okay, so again, is high resolution the future? It just so happens that I have been involved as one of the PIs in NextGEMS. And so I'm here to really tell you some of the things that we have done to try to characterize sources of biases that still exist in these high resolution simulations when it comes to tropical precipitation. So just a few words about the NextGEMS consortium. Again, it's EU-funded H2020. We're talking about a consortium of many, I forget now how many partners, but definitely more than a dozen, whose goal is to develop 2 next-generation Earth system models, IFS and ICON. And again, here I want to emphasize that both are coupled, developed at storm resolving resolutions. What is storm resolving? Well, it remains a bit unclear. We will see that we didn't get much. Right now we have simulations, multi-year simulations at 5 to 10 kilometer resolution. So really, in many ways, we're still here, really in the gray zone, where switching off completely deep convective parameterization might be arguable. So of course, one of the advantages of this high resolution simulations is that they explicitly represent the essential climate processes, such as storms, convection, ocean eddies, that existing climate models now either ignore or parameterize. And after prototype short-term simulations, NextGEMS produced the first multi-decadal simulations. Here, I just want to show you what the timeline has been. We have had 3 development cycles, all followed by a hackathon where we all met and hacked the data to look at the most recently available simulations. And these all led to the start of productions run with cycle 4. And again, this is the duration of the simulations that are now available from ICON and IFS. And again, I'll focus primarily, well, it's not true, but let's just let me tell you a few words about the production runs. This is a 30-year run under a force scenario, SSP 3.7. Hackathons were a big part of the project. As I mentioned, these were, instead of having regular, more common, more standard project meetings where we would meet and each would present their own result, we met through hackathons, where again, we all met and hacked at the most recent simulation cycles. The hackathon concept is taking the world by a storm, and now it is a global hackathon is being planned in 2025. If you want more information, this is the link where The vision is that maybe people in Japan will start hacking at the data from their own high-resolution simulation. And as the day comes to an end for them, they'll pass over the scripts to people living progressively in the West all the way to North America. Let me just say that to me, this vision is really very ambitious and not very realistic. Adrian and I have had a very hard time using the same scripts at each successive hackathon, but good luck to them. As you can well imagine, another challenge has been dealing with the massive output from these simulations. And so this is something that has been developed through the project. And this was one of the goals of the project, learning how to handle this data. And so the project has converged through harmonizing the simulation output in a hierarchy of spatial resolutions on hill peaks. Hill peaks, because these models are on unstructured grids, and hill peaks has the advantage that these are all equal area grids, basically. And depending on exactly what you're interested in, you can look at different zoom levels. This is zoom 0. This is basically, you can see very coarse. If you're interested in just global means, that might be enough. So of course, you are reducing the how massive the data that you're looking at are. And this is instead a zoom level that is somewhat consistent with the native, the resolution, the highest resolution of the native. Another big important point that I want to make, let's just say that there was the illusion, I think, there was the belief that you could take these models, run them at high resolutions, and they magically would not leak any energy nor water. That has not been the case at all. The first cycles had massive leakage. Cycle 4 simulations are a bit more consistent. And here I'm just showing the seasonal cycle of the top of atmosphere radiative budget versus surface temperature for icon 4 in blue. You see that all of these thinner lines are progressive years in the simulation. IFS is in green, and the cirrus is in gray. We can spend a lot of time looking at this plot, deciding which one has a better agreement. For sure, again, notice that this is a figure 8, and this is because in the part of the cycle where, and this is work by Thorsten Martzen, in part of the cycle where the basic surface temperature are cooling the top of atmosphere, warming the top of the atmosphere, radiative fluxes are, as so basically, as you go through the seasonal cycle, basically your top of atmosphere radiative fluxes decrease as the temperatures increase, and then you see the opposite behavior. Again, you decide which one is better. Maybe in terms of the overall range of the seasonality, IFS is better, but in terms maybe of the sum of the actual values, maybe icon. Again, that is to say there are still biases that exist even from the perspective of the top of atmosphere radiative budget. That is one of the things that developers really spend a lot of time looking at as the model is being developed and tuned. Here, the question that I really would like to address, and those was one of the underlying questions motivating this project, if we push these models to high resolution, can we remove mean state biases that have persisted through generations of climate models? And of course, one bias that has been very, very stubborn is the so-called double ITCZ bias. It has to do with how these models produce the tropical rainbows that we spent a lot of time looking at in the past few days, especially over the Pacific Ocean. Again, here, this is one way to look at the distribution of precipitation in the tropics, basically the 20% wettest regions on Earth. And the black line represents that measure, everything is within this 20% wettest region from IMERG, and the shadings are from icon on top, IFS at the bottom. And I hope that everybody probably can see, and will see many other ways of characterizing this, that for icon, for instance, we see that basically precipitation, and this is true throughout the equatorial region, is severely underestimated, and we will see through different metrics that precipitation south of the equator is grossly overestimated. That is to say, double ITCZ biases remain large. I don't have a CMIP curve here, but let me just say that ICON is way worse than CMIP, and IFS is not much better than CMIP. So again, here the black line is ERA 5. Again, here we can debate at length to what extent ERA 5 is an observational record, but it doesn't do too bad relative to GPCP in terms of this, this pattern where we definitely see a little bit of a dip, a minimum local minima, which is not too extreme in precipitation at the equator. Again, the ITCZ, the maximum precipitation at north of the equator, and this secondary broader precipitation zone south of the equator. Again, the different curves are the different IFS and ICON runs. Again, notice how all of the next-gen models, more or less, grossly underestimate precipitation at the equator and overdo precipitation south of the equator. Let me also emphasize, and here I'm focusing on ICON, in many ways, and this is something that Bjorn Stevens always likes to say, IFS has been used operationally for many years now, and so in many ways, probably it was more ready to be pushed to this high resolution. Although I do think, and Adrian here can correct me if I'm wrong, that IFS operationally is still used in its hydrostatic configuration in next gems. It's a non-hydrostatic version, which of course is needed when you go to these very, very high resolutions. Whereas ICON is a newly developed model, has been used less, and so it's the one that is prone to more surprises. And the one surprise that has emerged is how bad it does in terms of representing tropical precipitation. And so here I'm presenting the simulated monsoons. Again, here I'm using the shading is precipitation from GPCP. The winds are from ERA 5 in the bottom panel. For JJA, this is for DJF. The top panels represent ICON cycle 4, ICON cycle 3. Again, I'm gonna toggle between the two. And again, compare the monsoons that are simulated by ICON with the observed monsoons. So for sure, we do see this migration of the ITCZ over the subtropical summertime continents, but there's plenty of biases. Biases that I want to point your attention to is the fact that, for instance, the Western African monsoon extends basically all the way into the southern part of the Sahara. Notice how dry the Western Arabian Sea is. Notice how overdone is this secondary precipitation band south of the equator. If we move, again, here we can decide if our North American monsoon is better. Probably this is a region, I haven't looked at that, and so maybe this is something that we should do. Probably this is where your high resolution is giving, you gain something from the high resolution. Going to the Southern Hemisphere monsoons, again, I'll let you look at all of these biases, but notice how wet basically almost the entire continent of Australia is. So there are significant biases. Okay, so what tact did we take to understand a little bit better where this still outstanding biases come from? Surprise, surprise, we decided to take to use the atmospheric energy budget, both to look at zonal mean biases and also to start saying something about biases in the monsoonal precipitation. Here, I will just very, very briefly summarize things that Spencer has already introduced. And so through basically this budget really emphasizes how the ITCZ, because it is embedded within the ascending branch or ascending branches of the Hadley cell, really participates to global energy transport and the global energy budget. And as we already saw last time, in the presence of any hemispheric asymmetry in the net energy input, that is the energy that enters from the top and from the bottom of an atmospheric column, in the presence of any asymmetry in the net energy input here, I'm just schematizing what actually happens to be the situation for present day annual mean climate, where we have the northern hemisphere that are receiving more energy than the southern hemisphere. Then the ITCZ is sitting north of the equator because the Hadley cell is an energetically direct circulation that transports energy in the direction of its upper branch. Let me emphasize, and this is something that has not been brought up yesterday, how, again, this framework has really emphasized the anti-correlation between the position of the ITCZ and the cross-equatorial energy transport. Anti-correlation because, A positive value of the latitude of the ITCZ corresponds to a negative, that is southward cross-equatorial energy. However, again, let me emphasize, because this is one big assumption that we don't see persist through the seasonal cycle, this framework really assumes that basically changes, again, in energy transported by the Hadley circulation are all occurring through shifts of the ITCZ and changes in the mass overturning, without any changes in the efficiency with which the Hadley circulation is transporting energy. Let me just say that that is not always the case. The other thing that Spencer yesterday very nicely discussed is the fact that this framework has always also led to the introduction of a new proxy for the ITCZ, which is not based on precipitation, it's just based on the energy transported by the large-scale circulation and the Hadley circulation. Again, if you assume that eddies don't participate to the transport, and in particular, the energy flux equator is the latitude at which the mass and energy transport by the Hadley circulation go to zero, which again, do not always coincide, nor do they coincide with the ITCZ, but at least the assumption here is that variations in the energy flux equator give us an idea of variations or are correlated with variations of the ITCZ. So Bishop and Snyder 2014 was already cited yesterday. I want to go maybe a little bit more in the details of what they did, basically by just doing a first order Taylor expansion around the equator of the atmospheric energy budget. They came up with an expression for the position of the energy flux equator. This is the latitude of the energy flux equator, which we're going to assume is the latitude of the ITCZ. Big assumption there. And so they argue that this is, with the minus sign, linearly anti-correlated with the cross-equatorial energy transport. This is the value of the energy transport right at the equator, and inversely related to the divergence of that transport computed at the equator. That for an annually averaged atmospheric energy budget is also equal to the net energy input at the equator, because the slope of the energy transport, which is the divergence of the energy transport, is nothing else but the net energy input. And let me really emphasize what they tried to argue here through the schematics, and which is actually consistent with this analytical expression for the energy flux equator. Again, let's suppose that we start with the black line. This is the transport of energy with an energy flux equator where this transport goes to zero, and this specific value of the cross-equatorial energy transport. Again, the atmospheric energy budget has also emphasized that, for instance, if you perturb the system, even at latitudes remote to the ITCZ, the system will respond by adjusting the required energy transport, and it does so by basically shifting this curve without any changes in its slope, without changing the net energy input. Again, here, we're just assuming that this is a perturbation that requires a southward transport across the equator, which implies a northward shift of the ITCZ. However, Bishop and Snyder also emphasized that in reality, not all of perturbations will result in that asymmetric distribution. There are some, such as, for instance, El Nino, that are more symmetric. And in fact, what actually happens is there you can change the net energy input close to the equator, therefore changing the slope of the cross-equatorial energy transport, and this will give rise to a shift in the ITCZ, even without any change in the cross-equatorial energy transport. And again, this analytical expression captures both the dependence on both of these parameters. Okay? Again, here the important message is that the cross-equatorial energy transport is a measure of the hemispheric asymmetry in the net energy input, even at latitudes remote to the ITCZ. If the net energy input is symmetric above the equator, the ITCZ would sit right at the equator, and we would have zero cross-equatorial energy transport. Okay? Whereas the net energy input at the equator is what happens close to the equator, is the local influence on the ITCZ through the global energetics. Okay, so here again, we're going to be focusing, and I think I'm going a little bit slow, so maybe I'm going to just be focusing on the zonal mean analysis here. And maybe I'll just summarize briefly the analysis on the monsoon, but basically metrics that have been introduced to link ITCZ precipitation metrics to energetic metrics, as for instance, the precipitation centroid, which is basically just the center of mass, the tropical precipitation distribution. And but that is a bit harder to really correlate the precipitation centroid to this energetic framework, also because we see that, again, these distributions are somewhat complex, right? And so two other indices or metrics have been introduced by Adam et al. In 2016, an hemispherically anti-symmetric component. And this is basically just a normalize, you normalize, so that is really just measuring biases or properties of the distribution, not the amounts of precipitation. This is basically a metric that captures the asymmetry if you have more precipitation in the northern relative to the southern hemisphere. So just to look at possible cases, if the distribution of precipitation is perfectly symmetric, this index is equal to 0. If we have precipitation just sitting north of the equator, this is equal to 1. If it's sitting south of the equator, -1, and intermediate values. You get the picture. But then we also have an hemispherically symmetric component, and notice how this is defined as the equatorial precipitation normalized by the tropical precipitation -1. So what is this telling us? If again, precipitation is symmetric about at the equator, this index is equal to -1 for a tropically uniform precipitation distribution in the tropics. CP is equal to 0. And as the equatorial precipitation becomes more peak, this index increases. Okay, and basically, Adam et al. Argue that for hopefully things that I already discussed at length, this hemispherically antisymmetric component would be more directly related or anti-correlated with the cross-equatorial energy transport, and the equatorial precipitation index more directly related to the net energy. Okay, so again, let's go back to the ITCZ. I want to show you a little bit how we infer all of this different energetic metrics. So this is the energy transport by ERA 5, and all of the different lines are IFS and ICON. If you look at these lines, except for this one, which is an earlier version of ICON, you could say, well, no, this is not too bad, right? We see the transports more or less peaking at the right latitudes with more or less the right magnitude. If you start zooming in close to the equator, this is where you see a large spread. Notice a large spread in the value of the cross-equatorial energy transport, large spread in the energy flux equator, but also you see that, again, these lines are not all parallel to each other, nor are parallel to the ERA 5. This is indicative to biases in the net energy input close to the equator. Okay, this is to go into my precipitation metrics. Again, I did put in here, this is where ERA 5 is sitting in all of this. So these, again, all of the simulations that we have available. Let me emphasize that some of these are really, really short. We're talking about 1 year, 3 years, 5 years. We can discuss to what extent they really are representative of climatological conditions, but this is what we have. We try to use the ensemble that we had. And so again, notice how this is the asymmetric precipitation index, and notice how most of the models, because they overdo precipitation in the southern hemisphere, that tend to have a smaller value of this antisymmetric precipitation index relative to ERA 5. But we find a somewhat nice anti-correlation between the two, supporting the theory. If we look at the relationship between this equatorial precipitation index versus the absolute value of the net energy input, you see that this is a little bit all over the place. We don't see any obvious correlation. But then again, this is where the color coding of the different models through the different cycles start being somewhat important. You see that ICON is sitting somewhere here, so you start seeing some correlation there. And this is different cycles of IFS. It turns out that when you globally average the net energy input, maybe because the ocean is not balanced, this does not average to 0. So then we tried to compute the net energy input at the equator relative to this imbalance, and this is what we get. Now we get a much better correlation. And again, this is really to tell us, and again, this is an analysis that is still ongoing. I don't want to bore you with all where the different biases come from, because the latitudinal pattern is somewhat complicated. But again, here we are able to somewhat attribute biases in the asymmetric precipitation index. This is the fact that we have this excess precipitation south of the equator because our net energy input is more symmetric than it should be. And ICON and IFS, again, give biases that, depending on the specific latitude band you look at, can originate from clouds, can originate from surface fluxes. We also see that the fact that the equatorial precipitation is so underestimated in ICON and IFS relative to observations is because they don't capture well the net energy input at the equator. And the largest sources of bias there is the latent heat flux. And this is something that Adrian pointed or mentioned today, especially over ICON. The biases are very large. Let me emphasize how to make a point that I agree with that Dave already made. ERA is, ERA, the underlying model producing ERA is IFS. So one might argue that there, maybe we're not looking at completely independent samples. But here, the important thing is that, of course, despite the fact that ERA is not the observations, ERA has a lot of biases, it is the one reanalysis that we have that allows you to look at multi-decade climatologies. So we make the best use that we can of what we have. Let me also emphasize, however, also to get a better sense, of course, of the uncertainty associated with what we know about the observations. We'll be using CERES. We'll also be using satellite-retrieved turbulent surface fluxes. The problem is that, of course, those are available over the ocean, over land. It's a bit more complicated. So can we apply the energetic framework to the monsoons? I'll wrap it up, I think, in 5 minutes. This is where we need to be a bit smarter because now we are not in a basically 1D world where everything is averaged in longitude. And so we personally have not been much smarter, but we just digged a little bit into the literature. And in fact, a lot of people, including Booth and Cordy, have tried to extend this one-dimensional energetic framework to consideration of variability in longitude as well. And so again, here I'm just rewriting this equation that we have seen many times, stating that any net energy input into the atmospheric column needs to be balanced by divergence of the vertical integrated atmospheric energy flux. But now this is a vector, right? Because we are considering both zonal and meridional transport plus any storage. We've been trying to compute this term directly from the simulations. It is a very hard problem. As Spencer mentioned, closing these budgets, especially offline, is really complicated. So the way we do it, following Booth and Cordy, we're just saying, okay, let's just assume that the budget is indeed closed. And so now from the net energy input, we can define an energy flux potential whose Laplacian is equal to the net energy input. So this is a scalar quantity. But if we take the gradient of the scalar quantity, we get the implied zonal and meridional energy transport implied by a closure of the energy budget. And so this is what I'm showing based again on GPCP, the shading, precipitation, ERA 5 for all of the other energetic metrics. And so the line here represents this energy flux potential, and the vectors represent the energy transport, both in the zonal and the meridional direction. So I want to really point your attention to the fact that here in the annual mean, we have this broad minimum in the energy flux potential. This is where the divergence of the atmospheric energy transport maximizes. Other energy-based metrics, one that were introduced, one that we already know is the energy flux equator. Now, of course, we're not taking any zonal mean, longitude by longitude. We're looking at where the meridional energy transport goes to 0. But then we also have the so-called energy prime meridian or meridians. This is where the zonal energy transport goes to 0. And again, here we're taking into account the fact that in response to different forcings, we not only have meridional, but also zonal shifts. And again, this maximum, this minimum in the energy flux of potential is where, of course, we have the prime meridian and the energy flux equator meet each other. And notice why it is true that on average, precipitation is primarily collocated with the energy flux equator, we see that precipitation is particularly intensified along an energy prime meridian. And for instance, work by Bill Booth has clearly showed how it's really the energy prime meridian that captures shifts in precipitation in response, for instance, to the ENSO cycle. Okay, so to go back to the Northern Hemisphere summer monsoons, as simulated by ICON, whose biases I've already described, this is where we try to do the same computation now for JJA. This is the comparison with the observation. Again, we do see that in general, again, if we look on the large scale, we do see some good agreement between the observations and the simulation, again, over the South Asian, I should say, the Asian monsoon sector in JJA, we see this maximum, this export of energy by the large scale circulation. The same is true for DJF. Maybe we already start seeing that this excessive precipitation here over the Indian Ocean, Northern Australian, Western Australian region relative to observation is accompanied with westward displaced energy prime meridian. But this is just to say that, again, the biases that we see capture coarse aspects of the biases in the precipitation, exactly how we can use more smartly to make more quantitative assessments or links to the precipitation is something that we're still working, and that maybe the energy budget cannot tell us. So one advantage is, though, of the, again, let me show you here the model biases. This is JJA, DJF. The line here that you see is the bias of the energy flux potential relative to ERA 5. The shading is the bias in precipitation. And so you see that, again, on average, we have this collocating, again, over the Indian monsoon region, we do not see very large biases in the energy flux potential. Those seem to be collocated with this very excessive bias of precipitation over the Western African region. Although, again, the region of bias is enclosed in this zero line here. So it's a very broad region. If we look at DJF, again, we see that now this minimum, the overly emphasized minimum in ICON relative to ERA 5 is occurring over a very broad region that, while somewhat coincides with this excessive precipitation almost everywhere in the Atlantic, the Indian region, Australia, South Africa. But again, there is a collocation, but it's a little bit hard to, again, link in a one-to-one way biases in precipitation to biases in these energetic metrics. But one advantage is, even if you don't necessarily believe in this quantitative, what these biases can quantitatively tell you about precipitation biases, one of the advantages of this method, of this framework, is that it is linear. And what this means is that now we can decompose, we can look at how all of the different fluxes that give us the net energy input contribute to the total bias in this energy flux potential. And this is what I'm showing here, JJA, DJF. This is the total bias in shadings. This is exactly what I've shown here in the line contours. And this is the component due to biases in the top of atmosphere radiative fluxes. This is the bias due to the surface fluxes, both radiative and turbulent enthalpy fluxes. And this is the bias due to latent heat fluxes. And so again, we still don't fully understand exactly why we have this zonal pattern in JJA. There is also a zonal, kind of a dipole pattern, but maybe there is also a meridional structure in DJF. I don't have an answer for that. But the one point that I want to make is that in JJA, it seems that the largest portion of the bias comes from top of atmosphere radiative fluxes, whereas in DJF, almost all of it comes from surface fluxes, and a large portion of it is from the enthalpy, the latent enthalpy fluxes. And again, just to show you how large the biases are, this is what I'm showing here. Again, biases are large not only over the ocean, but also over land. Adrian has done very nice analysis comparing latent heat fluxes simulated by ICON in low wind regimes compared to buoy observations. And I think we have an answer for what's wrong in the parameterization of latent heat fluxes over the ocean on ICON. I think that this large biases over land point to other problems, even maybe how the model was initialized. I really do not know. Again, here, let me just go to my summary. A lot is happening. The urgent need for accurate climate information is leading to a variety of proposals for the future of climate modeling. One of these proposals leverages K-scale Earth system models. Despite increased realism, significant mean state biases still exist. The energetic framework, we believe, provides a useful way to analyze biases in tropical precipitation, especially in terms of its distribution. Relative to ERA 5, largest biases arise from surface fluxes rather than top of atmosphere fluxes. A lot more work needs to be done. And here again is my final statement that goes back to this question: what should we do in terms of a community? I really think that confidence in our projections really requires fundamental understanding. We cannot have confidence in those projections if you don't have theoretical frameworks to interpret our projections. And this is why we cannot forget about hierarchical approaches is that really leverage the whole hierarchy. I'll stop here. Thank you.
Question. Student questions? Participant questions? No, but he's not a student. Well, life.
Thank you, Simona. How quickly do the biases emerge in these next GEMS runs, right?
Quickly.
Yeah. So
quickly in a matter of months. And that is where it would be nice if we could potentially run the model ourselves, but that is not a capability that we have. It's not easy to port these models. Those are run. So the one advantage, we do have direct access to the KRZ, which is basically the German supercomputer, where the output is stored. Some of the simulations are run there. Some others are run on Lumi, which is, I think, a Finnish machine. But again, running this coupled model is something that is not easy. Let me just say that absolutely the fact that this biases emerged relatively quickly, of course, has led to MPI trying to take a step back, forget a little bit about the coupled runs, and perform fixed SST runs. And so this is where we are right now. We have access to the SST runs. We haven't had quite time to look at them yet. But this is where, again, some tests were done, for instance, to test the sensitivity of the latent heat fluxes, well, I should say the enthalpy fluxes to the existence of a gasiness factor. And increasing that gasiness factor has really led to a reduction of the double ATCC bias. But again, I don't think there is yet a version with that. Also because, again, the just increases, just multiplied by, I think, a factor of 16. And as you know, I mean, you should do things a little bit more systematically. Yeah.
I should know this actually. So when you show the energy flux potential, you quite rightly said we assume that the budget's closed. The other thing to mention that I think you didn't say is that we also assume there's no storage. That you're
Now the storage can be computed. I didn't compute it, but the storage, when we publish a paper, the storage we can compute. We have all of the.
Because
it's really
these calculations are assuming no storage.
No storage. These calculations, preliminary calculations, don't have any storage.
How short a timescale we can go and still make that assumption? Because at the moment we're showing 3-month averages there.
Actually, I don't think that the storage is going to be.
It's not going to be a big impact.
My gut feeling is that it's.
Okay.
Maybe it can change some aspects, but I don't think it's gonna. It's really the leading order there.
Just out of interest, because I'm not actually kind of in Next Gems itself, you mentioned the kind of 10 million budget, which was the EU funding.
Yeah.
But I presume that's mostly personnel and the kind of computer resources. Kind. Have they ever done a calculation of what the expense was in terms of all these runs?
Maybe they have, but I am not aware. Yeah, this I should say, this 10 million basically just went into personnel. Absolutely, we all got a postdoc, and of course, and in fact, a lot of people are working for free, right? In the sense that I do have a PhD student who's funded from another project looking at extremes, precipitation extremes over Italy from NextGen. So a lot of us are working. But I should also mention, that's one point, the data are available to the community. You need to sign up to DKRZ, but yeah, the idea is that the data, I'm not sure if they are, no, I think they are available, right? A project. You have to say how you're going to use the data, what you need it for. But the idea is that, again, as we become, also because we are struggling with looking at all of the data, more and more simulations are becoming available. Again, I just talked about the next gen simulations, but with IFS, there are other two projects, ERI and Wormwood, looking at coupling with different ocean model, PLASM and NEMO. So there is a lot going on. We have a lot of simulations. The data is massive. We're struggling to keep up. Arturo.
Okay, thank you very much. I was wondering, I guess there is not much funding to put a network of observations which could help reduce the bias, or at least measure the biases that we have all over the world. So let's think that we have the best, I mean, the ideal world in as ERAS 5 can give us. So let's have that as the best possible thing, or to close to reality. And I was wondering if some of these models from GEM could be you could locate where they are having troubles by doing some assimilation of this of ERA 5 as if it were the real world, and then see the sensitivity of the outputs in these gems, so that you could locate where the physics is struggling.
Yeah, I think we already have a good idea where the physics is struggling, right? In the sense that already looking at where the biases emerge is a good indicator of where things are going wrong. Of course, it's a bit harder to establish causality, right? In the sense that the system is, of course, coupled. Here we're saying that, of course, ICOM struggles in low wind regime regions, but of course, where the winds are very low is where the ITCZ is located. So the system is coupled, and it's a bit of these energetics, right? I think that when you are looking at things that happen away from the equator, maybe you can say, okay, but those don't have anything to do with how the cloud field is represented close to the equator. But then when you start looking at the net energy input, the net energy input depends on what the clouds that you develop, where the ITCZ is located, the winds that, of course, feed into the ITCZ. But I think that, again, we already, so that to answer your question, I do think, and I was asked this question last week at AMS, so where should we invest in terms of observations? I do think that continuing to measure as well as we can the top of atmosphere radiative budget is fundamental. Again, when we think about cross-equatorial energy transport by the atmosphere in the ocean, one calculation that has been done by Trendbeth using reanalysis just leverages the top of atmosphere radiative flux imbalance, right? Because whatever imbalance exists needs to be made up by the circulation, the general circulation of the atmosphere and the ocean. When we partition the cross-equatorial energy transport within the atmosphere and the ocean, we're looking at very, very small numbers that are, well, smaller than the uncertainty associated with our measurements. So I think that that's, and the other thing that I think we should really invest on is measurements of the turbulent heat fluxes. I think this is really where there is a large gap there.
You mean at the surface?
Surface,
Okay.
surface, absolutely. Okay. In fact, you know, I did participate. I was just a guest, not really participating to the science team, but big NASA proposal to measure winds over the ocean at high accuracy, with the idea that maybe this could help us develop better. Of course, this would still be an indirect measure, but get a better idea of the fluxes from the surface. But I think this is really a big gap. This is where there is still a lot of uncertainty, even from the observations. Anyway, the big project submitted to NASA was not funded, unfortunately, so we'll have to try again.
So great talk. Thank you so much. I really enjoyed it. Well, when you increase the spatial resolution, it comes with a lot of problems, you know. For example, the high model intercomparison project. We learned about it that the tropical cyclones are stronger and are unrealistic. So I don't know. I think that the spatial resolution is not everything. But I would like to ask you, for example, if you think that in the future, the global models will be something like a convection permitting, like something crazy, like a 3-kilometer spatial resolution. Or what do you think is coming next? Thank you.
So anyway, here I have my summary of the pros and cons, right? Pros of high resolution, more granular information that is at the local scale. We can improve numerics and of course reduce the number of polarizations needed, and sessional climate processes are resolved. Focus can be diverted, right? When you go to high resolution, there are certain things that you don't need to parameterize. And so maybe the focus can be diverted to other aspects of complexity, which still require parameterizations, and hopefully they are energetically close and consistent. But again, the cons are, as you rightly said, high resolution does not guarantee improved fidelity or fitness for climate simulations. High computational cost does limit calibrations and testing. High computational costs limit creation of large ensemble for uncertainty quantifications when we look at extreme events, such as tropical cyclones. 30 years might not be enough to really understand how they respond to climate change or to get, and as you said, just pushing to higher resolution doesn't give you a better statistics of this extreme events. And then, of course, the tools RMS. So I totally agree with you. At the same time, I think that, of course, these high resolution models are here to stay, right? We are getting to a point where now we can run for a limited time. We cannot still run 100-year simulation or go back in time and analyze paleoclimate simulations. But if you want to do, rather than just the time, but if you want to do kind of the, if you want to cover a time period, we cannot run the simulations. But they're here to stay, right? And I think that it's part of the community. We'll keep investing on this. So the one thing that I want to say is that, again, here we have to be a bit careful about, for sure, these are not convection permitting simulations. These are, well, I don't know, what's the convection resolving? Maybe they are convection permitting, they're not convection resolving, in the sense that they permit some forms of convection. Definitely, they do not resolve all of the scales involved with convection. So we start looking at mesoscale organization of convection. This, of course, is missing in current climate models. But again, as we saw, just increasing the resolution, even in terms of mean climatology, is not solving all of our issues. Yeah. And also, the other thing that I want to say, ICON does here, the simulations that I show, we do not have any parameterized convection. In IFS, they did retain some part of the mass flux shallow convection parameterization, because we are at scales that are still coarse enough that if you don't do that, you get this precipitation bombs. Really, they hate the word bombs, but they really are precipitation bombs at the.
Hi, Simona. Really, really nice talk. I think I have a question related to these hierarchical models. And in your opinion on these variable resolution models like MPAS that you can have like convection permitting in a really localized system, like just any monsoon in the world, but then having like, of course, a resolution
Where you don't
elsewhere.
need it.
And I think those are like, or at least in my sense, I think it's like an easier way to have like more runs just for testing the hypotheses. You're like, for example, just changing like topography or like in the brand, comparing like with the, but what's your opinion on these like variable resolution models? Do they have any?
I've never used them. Again, as you mentioned, MPAS is something that the US community is really investing on. And I think that it was born, where is the funding coming from? Do you know, Spencer, MPAS? Because MPAS was developed originally at NCAR. Now I think it's DOE that has taken over, but I really do not know. So I do think that those are great tools to use. I personally don't have any experience with them. And I don't even know how much it has really picked up. I haven't seen any results personally myself. So I don't know. Again, I do think, again, this is my, that again, so as always, right? The question is, we have these different tools. And I think that the important thing is to think about what tools are fit for whatever purpose you have, right? So this is really important. And so, of course, if I personally, and I've been lucky so far because I think my community has allowed me to do it, my funding sources have allowed me to do it. I personally have used climate models, including complex CIMIP models, including next-gen models, not to tell my local politician, this is what you need to do, this is what you need to prepare for in 30 years, but to test hypotheses. And I know that I'm in a lucky situation where I really use these models primarily, for problems that are driven by intellectual curiosity. As a community, we need to do better. We need to do better, right? As a community, absolutely. We need to provide accurate information that can provide guidance for how we adapt, how we mitigate the climate change that is clearly ongoing. And so this is where I think that we cannot just put all our eggs in one basket. This is where we need, with, of course, being conscious of the fact that the resources are not unlimited, they are limited. I think that, again, we cannot just decide high resolution is the way. We could have global high resolution, again, for certain problems, this, this, how is it called, telescoping, telezooming, whatever, approaches that allow you to follow and then zoom in the features you're interested in. When you're looking at, again, extreme events like tropical cyclones, that's definitely the way to go. For testing hypothesis, you don't even need that. An aquaplanet might be, a T42 might be all you need. And so this is where I think really we should, and of course AI, we should really, again, just not put all our eggs in one basket. We might realize 30 years from now that was the wrong basket.
One more question, please.
Sure.
I'm sorry
No, that's okay.
to abuse their time and your time.
Yeah, that's okay. It's okay.
Yeah.
But that's why I'm here. It's great.
Well, and we haven't mentioned the lower and upper stratosphere, and I was wondering because there is this reanalysis from the Japanese that go to the mesosphere, I think, and I was wondering if we could have it like a constraint for models. I mean, of course, these models that you mentioned don't cover that. I mean, their top is maybe 10 millibar at the most, probably.
No, I think they go beyond that. I don't know, not the mesosphere, but for sure they have a stratosphere.
They have.
Yeah,
Okay.
absolutely. They do have a stratosphere. Yeah.
So I wonder if we look at stratosphere, troposphere interactions, then that would be another thing to look at just for testing the validity of models.
Yeah, that could be absolutely. I agree with that. I do think that people have been looking at the QBO, but I don't know exactly. I don't know exactly where we stand there, but for sure, people are looking at what happens in the stratosphere. Yeah. As you know, the QBO has a little bit, somewhat this benchmark to look at your gravity wave, drag parameterizations, and things like that. So the QBO is for sure something that malwars pay attention to. Yeah.
Just one more self-promotion.
Didn't I do enough?
No.
For you?
No. This is a new one. Actually, no. This one is new. I forgot because I just.
Sorry.
But actually, it was very relevant to what Christian and Arturo said. And actually, I guess too. But we worked with the guys at NASA Goddard with their models. I don't know if you know Saulo Freitas, the grill in Freitas, and basically it's a scheme that's sensitive that turns off when you get to higher and higher resolution. But what we showed in that paper, and it came out in GRL, and we insulted certain peoples who might be full of BS. They're still not getting that one. All right. But so we criticized like the Dynamo project and things like that, of pushing. And what we did find also looking at the different models and with the NASA Guard and the different resolutions was that once we got down to 1 kilometer, that gave the worst results. So anyway,
Actually, I think that the Japanese are really, I think, in many ways ahead of us. I think that I saw in some of these hackathon presentations results from global simulations down to a few hundred meters, so below 1 kilometer, and things improve drastically when you really go to those resolutions. But again, this is definitely not, even within the next MM, I don't think I will see a global model at those resolutions run 100 years. This is still a long way to go. Yeah. Okay, so I'll try to make this brief. Again, this is also another project. You'll see, you'll get tired of this energy budget framework after this week. But on delayed monsoon onset with warming, this is work that I've done. I put in there, although I don't think I have time to cover them, but also put in there simulations with high obliquity, with the same aquaplanet model I'll be talking about that I already talked about. And then Katrina Wee was my former PhD student looking at changes in the monsoon with warming. Anna Lobo was the more planetary-oriented student looking at the high obliquity stuff. But first of all, let me do some advertising. So I don't know how many of you are undergraduate students here, but I just want to say that at Trento, we have a master's in environmental meteorology and climate physics. And this is a double degree, which means that if you complete your master's, you get 2 master's degrees, one from the University of Trento, one from the University of Innsbruck. All our courses are in English. So the official language is English. Thank God I can teach in English. The first year is in Trento, and the first semester of the second year is in Innsbruck. And then the student decides where they want to do their master's. It can be Innsbruck, it can be Trento, it can be any other academic reality. Within Italy, within Europe, I have a student who's going to go and do her master's thesis with Sarah Kang at MPI. And in fact, she was also talking to Nicole Feldel in the United States. So this is to say that when it comes to the thesis that lasts about 6 to 9 months, there's many possibilities. Our applications are now open. This is the link. If you have any questions, if you're interested, let me know, because since September, I am the lucky coordinator of this program. Then some more advertising. I currently have 2 positions that are open. Those are 15 months position to work on a project funded basically by the Italian government. And it aims at looking at the Mediterranean heat budget and extreme transports, trying to tie extreme transports of energy to possibly extreme events, such as heat waves or droughts in the Mediterranean region, which is another area that is spending quite some time thinking about in the past 5 years. More information than the following website. This is effectively a postdoc position, but the good news is that a PhD is not required. So if you have a master's degree, you can apply. As Adrian mentioned, we also have 2 incoming openings to postdoc positions to study variability and response to global warming of the Western African monsoon, and in fact, more idealized monsoons. Please get in touch. The positions are not officially open yet. One is going to open hopefully in the next few months, the other next year. Okay, so then I promised I would go into the classes on scaling. I apologize to those of you who know what this is, but I also heard by talking with some of you one-on-one that not everybody has a background in atmospheric sciences. And I always, again, when I teach my thermodynamics, I always say this is possibly the most important relationship in climate science. And in fact, some of these things that I'll say today really connect to things that, for instance, Spencer discussed both yesterday and today. So let's recall the Clausius-Clapeyron relation. Again, this is just stating that the derivative of the logarithm of the saturation vapor pressure depends only on temperature, as stated here. So we want to use this fundamental relation to derive a scaling for fractional changes in atmospheric moisture with warming. You always hear this sentence: a warmer atmosphere is also a moister atmosphere. Can we be more precise? Let's recall that the specific humidity is equal approximately to the relative humidity multiplied by the saturation specific humidity, which is a function of temperature and pressure. Here we'll forget about the dependence on pressure. We'll look at the dependence on temperature. If we assume that relative humidity is mostly invariant, then fractional changes in specific humidity scale as fractional changes in the saturation specific humidity, which scale with fractional changes in the saturation vapor pressure. Okay, so how can we use the Clausius-Clapeyron relation to obtain order of magnitude of these fractional changes in moisture in response to a given warming? So I'm gonna rewrite the Clausius-Clapeyron relationship in the following way. Notice we're now just replaced the derivative with these deltas. Those are variations in response to a forcing. And I just express this as a fractional change in, okay? And so let's assume that temperature in response, for instance, to a doubling of CO2 increases by 1%. And why 1%? Because this corresponds to a fractional change, to an absolute change in temperature of 3 Kelvin, if we assume a temperature of 300 Kelvin. And this is, to these days, remains our best estimate of the equilibrium climate sensitivity. The increase in the surface temperature to a doubling of CO2 if we let the system adjust, if we give the system enough time to adjust again to equilibrium. Again, this corresponds to an absolute increase in temperature of about 3 Kelvin. Okay, so now we want to estimate the S over ES, the fractional increase in saturation specific humidity in response to this fractional increase in temperature of 1%. How do we do it? LV is a constant. RV is a constant. We just put in there the temperature of 300 Kelvin. And what you find is that is a very simple calculation that then the fractional change in saturation specific humidity is 20%. A 1% increase in temperature gives rise to approximately, again, here we're doing orders of magnitude, 20% increase in the saturation specific humidity. This is huge. And it, of course, relies on the exponential dependence on temperature of the saturation specific humidity. And now, again, we're going to assume that this is also a scaling for the specific humidity. If now you divide for the 3 degree Kelvin, you obtain the very famous Clausius-Clapeyron scaling that tells us that in a warmer world, moisture content increases at a rate of about 6 to 7% per each degree of warming. Okay? And again, this was the Clausius-Clapeyron scaling that was invoked yesterday to explain both mean and changes, mean precipitation changes and or extremes. Okay? All good? Okay, repetita iunt. Okay, so now let's move on to changes, possible changes of monsoon onset with warming. And so I spent quite some time, but I will let Adrian tell you all about this index for the onset of the monsoon that we introduced with my, again, former student, Jennifer Walker, in 2016. And let me emphasize how this work that, again, was aimed at introducing a new index for the onset of the monsoon, basically relied on work that we had done previously to define an index for the year-to-year variability of the monsoon. And here we are taking this large-scale approach where we're really thinking about large-scale changes in the dominant budgets in this broad South Asian monsoon region that spans 10 to 30 degrees north and 60 to 100 degrees east. And so in particular, this budget is based on the moisture flux converging into this region. And we look at changes through the seasonal cycle, and again, in a way that Adrian will describe in detail. And a little bit about the motivation of this index is because we wanted something that was not local, was representative of large-scale changes in the atmospheric circulation, but was still important for precipitation. And so that's where the moisture budget comes in, because we will see under certain assumptions, the net precipitation, the difference between precipitation and evaporation, is equal to the moisture flux convergence. So if you can say something about moisture flux convergence, you are saying something about the net precipitation. It is strongly constrained by circulation changes because, for instance, when you look at year-to-year variability in the moisture transport, that variability is primarily dominated not by changes in moisture that only account for about 8% of that year-to-year variability, but primarily through changes in the circulation. And so that is what we wanted to accomplish, something that was still relevant for people who cares about what the large-scale wind is doing, in terms of agriculture, many other economical activities, you care about precipitation, but was still somewhat indicative of large changes in the large-scale circulation. And again, this is something that you guys will see a little bit more in depth tomorrow in one of the hands-on. But here we compared our new onset for the monsoon, for the Indian monsoon. So this is basically the time for that specific year in which our newly introduced index detected the onset of the monsoon. And this was in comparison with other monsoon onset indices that exist in the literature. The blue one is the monsoon onset over Kerala. This is the standard traditional monsoon onset index that is used by the India Meteorological Department. It's basically precipitation arriving in this region here. Then we have the OCI, the onset circulation index, is an index that is based on the westerly winds at the 150 hectopascal reaches a certain threshold. And the hydrological onset and withdrawal index, Fasulo and Webster, is somewhat related to ours, but it's basically just measures the moisture transport when it goes over a certain threshold. The one thing that I will point your attention to here is that our onset is, so our metric, our index captures the onset with a lead of about 10 days relative to other indices. And we'll see why that is the case. And this is really maybe pointing to the possibility of doing something interesting with this onset in terms of predictability. Okay, but now going back to the onset is something I've been thinking a lot about. And also because, as Spencer already very nicely discussed yesterday, when we look at CIMI projections, the spread remains large in the amplitude of precipitation and circulation changes with warming. For instance, Western African monsoon is one region where the spread remains very large. But one robust response is the fact that the onset is delayed in almost all monsoon regions. And so what drives this delay in the monsoon onset? Or let me rephrase this question. Is the lengthy contrast really important? Is it really is it fundamental for this observed onset delay? And a few mechanisms have been proposed in the literature. Earlier explanations that rely on the differing response between the land and the ocean in terms of the energy and the moisture budget. A newly proposed mechanism, that is the one that will be done, emphasizes a mechanism that acts irrespective of the land sea contrast. Again, just maybe a couple of words about the model that we're using. Again, it's the Aquaplanet model we saw yesterday, and I think, only yesterday. And this is a let me just say that it's idealized not only in terms of its lower boundary, but also in terms of the physics that is being represented. Maybe the important point here is that radiation is treated as two-stream gray radiation with prescribed short-wave and long-wave optical depths. We impose a seasonal cycle of insolation of 360 days. We don't have any diurnal cycle. And so this model is extremely cheap. That's why we've used this extensively. It can be run in a wide range of configurations and climates. And so here I'm going to show you climate change experiments that we have performed with this model. And in particular, just by rescaling a parameter that basically scrapes the prescribed optical depth in the long wave, you can basically simulate increases or decreases in concentration of greenhouse gases. Alpha equal to 1 is our present day climate. And you see that by changing alpha, you can generate climates that go from much colder to much warmer than present day climate. And this is the change in the global mean precipitation as the surface is warmed. This, as probably we all expect, global mean precipitation increases. I won't discuss global mean changes because there have been studies in this model extensively through the years by Paul O'Gorman. Here we're interested in the simulated monsoons. And so again, this is the seasonal cycle of the simulated precipitation, starting from an optically thin atmosphere to a very optically thick atmosphere. I picked the same contours to show you again, the behavior. We clearly see that the amount of precipitation increases as the climate is warmed. Let me also emphasize how this solid line here is one of the many metrics that exist in the literature to capture the ITCZ position. And here you see that the plus sign is one metric of the onset of the monsoon, and the open circle is the retreat predicted by the same. And so I hope that everybody can see that as the climate is warm, precipitation, monsoonal precipitation increases. You also see that the position of this monsoonal precipitation band shifts further poleward. And then I hope that you can also see, but I'll be more quantitative about this in a second, the monsoon onset gets progressively delayed. Okay, so increase in intensity, again, here really super quickly because I want to focus on the delay. So this is 3 simulations, the solid orange line, present day climate, blue colder, dashed line warmer, for 2 different time slices in the warm season. Again, on average, we see that monsoonal precipitation increases. We also see that the monsoonal precipitation moves further poleward. Again, this is 3 different metrics to detect that ITTZ as a function of the global mean surface temperature. The red line is the precipitation maximum. This curve here represents the moist static energy maximum that we said is another indicator of where we expect maximal precipitation. And this is another metric based on, that measures some aspects of the precipitation distribution. Again, notice how throughout almost all of these simulations, the moist static energy maximum tends to sit poleward of the precipitation maximum. And then finally, monsoon onset. This is what we get. These are 2 different metrics of monsoon onset. This is just based, the crosses, the red plus signs, are just, again, the onset measured as the time at which we're focusing on northern hemisphere monsoon onset. That represents the time at which precipitation in the northern hemisphere subtropics exceeds a certain threshold. And the green circles represent the onset as measured by this Walker and Bordoni onset that you learn everything about tomorrow. I also want to show you circulation changes with warming. Those are interesting on their own. Again, colder climate, present day, warmer climate. And so notice how the circulation is such that as the climate is warm, the tropopause gets deeper. All of these circulations are such that they more or less in the monsoon season conserve angular momentum. This is something that we hinted at. I didn't quite tell you exactly how you can measure to what extent a circulation approaches or doesn't conservation of angular momentum, but just notice the pink lines are contours of angular momentum. Notice how in all of this cross-equatorial circulations, the angular momentum contours take a horseshoe shape that very well matches the streamlines of the returning circulation. Another interesting feature that I won't have time to discuss is that while the monsoon precipitation increases monotonically with warming, the circulation does not. The circulation is weaker in cold climates, increases with warming until present day climate, and then it starts decreasing. And this has to do with the fact that the circulation becomes deeper. There are changes in how effective it is at transporting energy. Okay, but now I want to focus on the delay in the monsoon onset. I'll evoke again the moist static energy budget. I'm sorry, the moist static energy or the atmospheric energy budget framework. I won't tell you again all of the indices that are based on this energetic framework. I will just say that everything that we have said so far neglects completely the possible role that energy storage plays. And so then the question that we wanted to ask ourselves, and this is because of previous work by Song et al., is storage becoming increasingly important with warming? How can we do this? How can we be more quantitative about this? So this is the energy budget that we've seen many times. The net energy input needs to be balanced by the divergence of moist static energy transport by the circulation, plus possibly any storage that exists in the atmospheric column. Remember, this is a vertically integrated budget. The interesting thing for a moist atmosphere is that energy can be stored in an atmospheric column, not just through its dry enthalpy component, but also through its latent energy component. And again, the Clausius-Clapeyron scaling comes in handy here because we have just showed how this is very sensitive. The amount of moisture in atmospheric column is very sensitive to temperature. So can changes in the latent energy component of the effective heat capacity of the atmosphere does it have anything to do with this delayed monsoon onset? And so again, here I am plotting for the different simulations color-coded from warm to cold for the 3 terms in the energy budget averaged in the subtropics of the Northern Hemisphere. Again, we're looking at the transition into the summer, Northern Hemisphere summer transition. So top, net energy input, bottom, the atmospheric energy flux divergence, center, bottom, atmospheric energy storage. And I hope that you can see that while in the cold simulations, the blue-green curves, any change at the beginning of the warm season and the net energy input is immediately accompanied by changes in the transport, in the export of energy by the atmospheric circulation. In the warmest simulation, there is very little change, and that is because it's the atmospheric energy storage term that increases. That net energy input doesn't go into changes in the circulation. It is stored in the atmospheric column. It is only later through the course of the seasonal cycle, as this storage goes to 0, that actually the circulation needs to do its part and increase its export and shifts in the position of the ITCZ into the Northern Hemisphere subtropics. We can be a little bit maybe more quantitative in the following way. So of course, from these simulations, actually, we can close the atmospheric energy budget quite well, and we can compute directly this term, which is what I'm showing here. This is directly from the simulation output. But now we can look at the transport that would be implied just by the net energy input, the transport implied by the minus the negative storage, if I were to put it on the other side, and the combined transport. And this is what I'm showing here, again, for the different simulations, for the different time slices, April and July. Notice how, again, on the top, I'm looking at the transport implied by the net energy input. To recap, if the net energy input is symmetric between the 2 hemispheres, we get 0 transport across the equator and a poleward transport in both hemispheres. But here we're in April, the net energy input is already asymmetric enough, of course, with a warmer northern hemisphere and a colder, I should say, the northern hemisphere being the hemisphere with net energy input, the southern hemisphere net energy deficit, that if the net energy input were to be balanced by the atmospheric energy transport, we would have negative southward cross-equatorial energy transport already in April across all simulations, and energy flux equator and ITCZ already north of the equator. But if you look now at the asymmetry in the storage, we see that, in fact, that term drives the opposite least sign energy transport across simulations, that in the warmest simulation is large enough that when we look at the combined effect, this is already still keeping the transport of energy northward, which means an ITCZ that is still sitting south of the equator for the warmest simulation. This is only later in July, as the storage decreases, that now, again, it's the atmospheric circulation that needs to do the job of exporting that energy from the northern hemisphere to the southern hemisphere, and it can only do it by shifting its ITCZ north of. Okay, so I think this is really pointing us to a very nice, simple mechanism. But then the question, what causes these changes in the storage term? As I mentioned, it's all about the latent energy. In fact, one can show using simple Clausius-Clapeyron scaling that basically this is proportional to changes in the surface temperature rescaled by an amplifying factor. But one other point that I want to emphasize is that one interesting behavior that we see in our simulations is the fact that in the coldest simulations, until we reach present-day climate, we see that basically the monsoon onset gets delayed in a linear fashion with warming, and then at one point in the warmest simulations, we see that it kind of saturates, doesn't change much. So can we come up with an explanation for that? And now I'm going to change a little bit perspective, and I'm going to take the perspective of the fact that, in fact, especially on seasonal time scales, precipitation very much follows the changes in moist static energy close to the surface. And so I'm going to be using a energy balance model, which is a two-variable energy balance model in EBM that has been studied in the literature with several applications, first by Barsugli and Battisti in 1999, and then by Cronin and Emanuel in 2013. So basically, this is really thinking about the coupling between the atmosphere and the surface. And here, the Ca represents the atmospheric heat capacity, which is this storage term that we discussed already. Ta represents changes in the near surface temperature. Ts represents changes or anomalies in the surface temperature. This is nothing else but a linearized Stefan Boltzmann equation. So this just represents the OLR, the outgoing long-wave radiation, and B is basically a climate feedback parameter. And this term lambda just represents the coupling between the surface and the atmosphere above it through surface fluxes. And so again, Cronin and Emanuel studied this model, properties of this model in radiative convective equilibrium. And so they basically just look at how the system would respond if you put in there an initial perturbation. In particular, they were interested in the time scale by which the system would adjust back to equilibrium. And they showed that the mode of variability with the same sign and nearly equal perturbations in atmospheric and surface temperature has an adjustment time scale that can, at the leading order, be approximated by the sum between the atmospheric heat capacity, effective heat capacity, and the surface heat capacity divided by this, basically, climate feedback parameter. Okay, so why is it important for us? Now we can imagine adding a seasonally varying insolation forcing with a given period, and we can define a parameter alpha that measures the ratio of the seasonal time scale, which is the inverse of the orbital period, to the thermal inertial time scale. So when alpha is much less than 1, what you are looking at is a seasonal time scale that is much shorter than the inertial time scale. When alpha is, what did I say? Did I say when alpha is much less than 1, the inertial time scale is much larger than the seasonal time scale. And so what this means is that basically the system does not have time to adjust to equilibrium. When alpha is much larger than 1, then you're just saying that basically the seasonal time scale is much larger than the inertial time scale, so the system adjusts promptly to equilibrium. And so this parameter controls the time lag between the seasonally varying forcing and the lower whatever temperature response. Again, when alpha is much larger than 1, this lag, this represents the lag between, for instance, the seasonal, the insolation forcing and the temperature response. Again, alpha much larger than 1, this is very small. When alpha is much smaller than 1, basically these two signals, you get a delay until the two signals are in quadrature relative to each other. And so the nice thing of this framework is that what determines this alpha, which is based on this inertial time scale, this is what we imposed at 360 days. This is something that we can diagnose from model simulations. So we can predict what is the time scale diagnosed from output from our simulations. And in particular, we can obtain the effective heat capacity just by regressing the atmospheric energy, the energy in the atmospheric column versus the near surface temperature, the same to obtain this climate feedback parameter. And so if now I compute again this time lag, this is what I get. These are the blue crosses, and notice how this really well captures the lag that represents basically how long it takes for the near surface temperature, and that is precipitation, to respond to the insolation. See? And so this is my summary. Idealized aquaplanet simulations show a robust delay in monsoon onset with warming, consistent with projections based on CIMEP models. And so this is not, again, one might think, right? This is just an artifact of the simplicity of this model, but I think there is something more fundamental that here also applies to beyond just an aquaplanet world. This delay is due to an increase in the energy stored in an atmospheric column through an increase in its latent energy component. A single EBM well captures this behavior and highlights the role that the increased effective heat capacity of the atmospheric column plays in the response of lower level temperature and precipitation to the imposed forcing. And importantly, these mechanisms acts irrespective of the land sea contrast. Because yesterday there was some interest, again, I won't have much time, but in the next 5 minutes, I want to show you simulations that we performed with a very similar aquaplanet model with shallow mixed layer depth, changing the obliquity. So this is, again, an Earth-like planet in any other aspect, but we start from present-day obliquity, and we increase it progressively, almost all the way to a completely tilted over planet. Again, and as I mentioned yesterday, the motivation is, first of all, because even within our solar systems, we have examples of obliquities that are higher than Earth. For instance, Mars has an obliquity that has changed erratically. Also, sometimes in the history of that planet going to high values. And again, this also, as I mentioned yesterday, it's really a nice test bed for a lot of the theories that we have developed, for instance, for the Hadley cell and what controls the position of the ITCZ. So for those of you who are not used to be thinking about what does actually changing obliquity do to the distribution of the insolation, both in its annual mean and its seasonal distribution, this is what I'm showing here. So again, here the solid lines, color-coded according to increased obliquity, show the annually averaged insolation forcing. So for low obliquity, we get the very familiar pattern: maximum close at the equator, minima at the 2 poles. But the interesting thing is that as we increase obliquity, that gradient flattens, and it's basically flat when you reach obliquity of 54. Beyond 54, you get that the equator is in fact a minimum in insolation, and the 2 poles become the latitudes where, well, it's actually broad range of latitudes where you get maximum insolation. And then the dotted lines here represents the distribution in northern hemisphere solstice. And the one thing that I want to emphasize is how much insolation the planet would get at the summer pole for 85 obliquity is more than twice as large, and the one at 23. And also notice how basically for 85 obliquity, the entire winter hemisphere is experiencing polar night, and even the low latitudes of the summer hemisphere are not receiving a whole lot of energy from the sun. And this is the temperature, which I don't want to comment too much because I want to show you the distribution of the simulated precipitation, 23 obliquity, 85 obliquity. If some of you are looking at this additional secondary band of precipitation that was there but not quite so pronounced in the previous simulations that I showed you, this is because these details are a little bit dependent on what you let the ocean do. And in particular, if you let the ocean do some of the work in transporting that energy poleward that is required to achieve balance with the top of atmosphere radiative fluxes, then this secondary precipitation peak decreases somewhat. But again, here we really wanted to see how much we can push the atmosphere to respond to these very large gradients in seasonal insolation. And this is what we get at 85 obliquity. So again, notice how the ITCZ embedded in the ascending branch of the Hadley cell becomes broader. It doesn't quite reach the pole, and yet the pole is a place where there is a lot of convective activity. Also notice how towards the end of the summer season, as the ITCZ is already retreating poleward, there is sustained precipitation over the pole. In fact, the pole is the maximum, is where we find the maximum in precipitation. Okay, so then the question here, what drives precipitation over the summer pole? I don't know if I have time to show this, but the one thing that I wanted to show you, because again, yesterday there was a lot of discussion about the Hadley cell, is the Hadley cells that are simulated for Earth-like and 85 obliquity simulation. Again, notice that even when we have an obliquity of 85, even if for sure the pole is the warmest place on the planet, and this is where moist-static energy maximizes, the Hadley cell does not extend all the way to the pole, remains confined within 60 degrees. And this is a little bit, there is a lot of indices for the precipitation that we put on this plot. Here, really what I want to emphasize is this is the precipitation maximum. The blue is really the precipitation maximum or the maximum within the Hadley cell is located. And then this gray line is the energy flux equator. This gray, this lighter shade of gray is this extent of the Hadley circulation. How do we measure the extent of the Hadley circulation? When you have Hadley cells that are more symmetric about the equator, it's easy. You just look at where the stream function changes sign. When these circulations become broader, it's a bit of an issue. The circulation never changes sign. And so usually you detect the extent of the circulation by just taking the latitude at which the stream function gets below a certain threshold, 5 to 10%. And this is the metric that we show here. But then notice how if we take the Moist static energy maximum again, even at 40 obliquity, it's really good. The MSE maximizes at the summer pole, even when the ITCC, again, interpret as precipitation embedded within the ascending branch of the Hadley cell, remains much closer to the equator. The other thing that is interesting, I'll stop here because I really don't have time, but this is just to say that there's a lot of interesting things when you start running the simulations in a much broader parameter space, is the fact that now we're looking at Northern Hemisphere winter solstice. This is 23-degree obliquity. Notice how we have a Hadley cell. This is again the winter cell. The summer cell would be here. And this is a Ferrel cell. At 85 obliquity, there is no Ferrel cell. And yet one would think, but this is, a climate where the seasonal cycle is much more extreme. And so why don't we have a Ferrel cell? Again, I leave it there. Okay, and so I'll stop here and I'll take any.
Okay, yeah, we should probably really head out because we violated the 5
true.
p.m. yesterday.
Well, maybe what we can do, keep any question for
Yeah.
tomorrow. We have time to interact tomorrow. And this was really to, motivate a broader, just to say how, again, this hierarchical approach really challenges our more conventional thinking.
So what I would say for you, for the people tomorrow again is in the sala audiovisual in our Instituto. So if you're not, there's people that are, I think 25 registered. Okay. So if you're really interested in getting in, well, there's the 25 that are registered that have, yeah, we might have some spaces. So if you're really interested in getting in and you're not registered for that, wait outside. And then if it gets too crowded, well, okay, sorry. Okay. But that's one, it's a possibility.
Is it